Okay, let's take a look at another proof where we have to do a proof by contradiction. So it says example 8, prove that for all sets A, B, and C, if A is inside B and B is inside of C complement, then A and C have nothing in common. It's equal to the empty set, basically. So there's the proof setup. Suppose not, that is, suppose that A, B, C are any sets with A is inside of B and B is inside of C complement, and that A intersected with C is not the empty set. All right, so we're going to try to derive a contradiction from this. Okay, since A intersected with C is not the empty set, then there must be an element X inside of there. There must be an X inside of A intersected with C. But this implies that X is inside of A, and at the same time X is inside of C. Okay, how do I know this? I know this because of intersection, right? So by definition of intersection, if you're inside of the intersection of A and C, then you're inside of A and inside of C. But wait a second. But since A is inside of B, then the element that's already in A is going to be automatically inside of B. So since X is in A, so X is inside of B. But also, we know that B as a set is inside of C complement. And so the X that was in B will now be transferred to C complement. This implies that X is now inside of C complement. But this is a contradiction, because how could X be inside of C and at the same time be inside of C complement? Remember, an element can either be in the set or outside. It cannot be both in and out. And this is saying that X is inside the set C, and this is saying X is not inside the set C. Right? So saying that X is inside of C complement means that X is not inside of C. So how could it be that X is inside of C and not inside of C at the same time? This is a contradiction. And therefore, the original assumption of the problem is true, and the theorem turns out to be true.